In this example on how to calculate molecular formula from empirical formulas, I wish to point out that you can only calculate the molar mass, rather the molecular formula, if you know the molar mass. The empirical formula can be determined if you have the percentage composition. That's as far as you get. You'll get the formula in lowest terms, but to really understand what the molecular formula is, you have to know what the molar mass is, so you'll know what to multiply the empirical formula by. So for example, determine the empirical formula of the compound with the following composition by mass. So we're given information that contains the percentage composition of each one of these elements. And the first step is to assume 100 grams of the sample, so that the percentages can be turned into gram amounts. So if we have 62% carbon in a 100 gram sample, then we know we have 62 grams of carbon, and so on down the line for all different elements. We then divide by the molar mass of each one of the constituent elements, which gives us a number. Each one of the numbers is then divided by the lowest number obtained in the ratio. In this case, the ratio of nitrogen is 12.1%. If we divide by 0.86 moles, which is the number of moles of nitrogen present in that 100 gram sample, we'll get 6, 6, 1, and 1.5. Now obviously we cannot have 1.5 atoms in a molecule, so it makes sense that to multiply that ratio by 2 to get whole number values. So the empirical formula in this case is carbon 12, hydrogen 12, nitrogen 2, oxygen 3. We can't go any further than that unless we're given the molar mass of the sample. And in this sample we're not. So that's where we have to stop. We found the empirical formula. Now if we were told that the molar mass of the sample was equal to the molar mass of this, then we would know that the empirical formula was the same as the molecular formula. In the next example, which is number 3, from chapter 3, number 47 of Brown, 10th edition, we're given an empirical formula, CH2, and we're told that the molecular formula has a mass of 84 grams per mole. So the first thing we do is find out how much the empirical formula mass is. In this case, it's 14. And when we divide the empirical formula mass into the molar mass, we get close to integer value, and this is normal for real life experiments. You're never going to get exact whole numbers, but this is very close to 6. When we multiply the empirical formula by 6, we get the molecular formula, which is C6H12. In the next example, we are told that the empirical formula is NH2Cl. And we find the molar mass of the empirical formula, which happens to be 51.47. We're told that the empirical formula mass and the molecular mass are the same. When that happens, then we know that the formula mass is the same as the empirical formula.
Sorry for this interruption. Teachers, please do not send students down for notes for yesterday's absences. Thank you.
And that brings us to the next subject we're going to broach, which is stoichiometry. The relationship between reactants and products in a balanced chemical equation is called stoichiometry. Stoichiometry is necessary because calculations involving chemical substances must be done using the mole concept, and that's because each element has a different mass and each compound has a different mass. So how do we relate quantities? So, for example, in the combustion of butane, when we balance a combustion reaction involving hydrocarbons, which are composed of carbon and hydrogen, we get only carbon dioxide and water as products. And the best way to balance combustion reactions is to do it alphabetically. First the carbon, then the hydrogen, and finally the oxygen. In the case of butane with 4 carbons, 4 CO2 molecules will be formed. It has 10 hydrogens, so 5 waters will be formed. And then we worry about balancing the oxygen. There are 4 times 2 oxygens here, that's 8. 8 plus 5 is 13, so we can write 13 over 2 to get 13 oxygens. If we don't like fractions in our balanced equations, we can simply double everything. And it becomes 2, 13, 8, 10. These coefficients are the stoichiometry of the reaction. If we were to write an English sentence to translate what this chemical phrase means, we would say 2 moles of butane react with 13 moles of oxygen to produce 8 moles of carbon dioxide and 10 moles of water, all of them in the gas phase. Which brings us to the first example question. 25.5 grams of butane are burned in the presence of excess oxygen. How many grams of CO2 and water is produced? And I point out here, there's a procedure that we normally follow in solving these types of problems. We can start from grams, but it has to go to moles, and then for moles we have to go to moles of some other substance in the same equation, and then for moles of that substance we go to grams. Anytime you want to convert from grams to moles, you have to divide by the molar mass. If you want to convert from moles to grams, you have to multiply by molar mass. Whenever you go from moles to moles within an equation, you have to go through the stoichiometry, which is the result that you obtain by looking at these coefficients. So if you want to convert moles of oxygen into moles of CO2 within this reaction, you know that the ratio is going to be 13 moles of oxygen are going to be used for every 8 moles of CO2 that is produced. To continue our calculation, our 25.5 grams of butane is divided by its molar mass to obtain the number of moles of butane. We then invoke the stoichiometry of the reaction to find out how many moles of CO2 are produced. So it's that many moles of butane with a stoichiometry of 8 to 2. 8 moles of CO2 produced for every 2 moles of butane consumed gives us 1.75 moles of CO2 formed. Then we find out how many grams of CO2 formed by multiplying this number by the molar mass of carbon dioxide. 1.75 times 34 gives us 59.7 grams of CO2 formed.